Hi. Welcome back. Good afternoon. This is my 8th period class, and it is currently the 28th of February. It's the last day of February, guys. Oh my god. It went so fast. So we're going to continue on with the roundest chapter in the whole year. Because we're talking circles. Okay. If I have to explain it, it stops being funny. Anyway, I'm trying. So the first day we talked about circles, we defined them, we talked about what they were, and then we talked about their circumferences. Day 2 of circles, we looked at the angles that they created, and then the arcs, those pieces of a pizza crust, basically, of our circle. Today we're going to continue on talking about arcs, but this time we're going to be talking about chords, the straight lines that go through the circle and create our arcs. So points are able to determine both chords and arcs, and this is how they do it, and this is how you tell the difference. Bless you. So if I have this point F and G on a circle, the straight line that connects them through the circle is the chord, and we write the name of that chord this way. Its name is line segment FG. Hi, ladies. Up here, please. Thank you. Now, if I talk about the arc, that is, I'm going to go from F to G, but instead of going through the circle, I'm going to stay on the circle. That is arc FG. Notice the difference in the way I wrote and said the names.
Yeah.
This is arc FG. This is chord line segment FG. Now there's one property that's super useful. In a single circle, or in congruent circles, two minor arcs are congruent if and only if the chords that are creating those arcs are themselves congruent. Notice what we said here. If I took a pizza and I cut from edge of pizza to edge of pizza without going through the center of the pizza, okay, so just sliced off part of the crust, and the length of that cut, I duplicated the length of that cut somewhere else on the pizza to cut off crust, the amount of crust I would have in each of my hands would be the same. Okay, makes perfect sense, yes? I had a shake of head. Talk to me. You're trying to picture. Okay. Okay. You refigured it, yes? All right. Let's look at number 2. Let's use this to help us figure out how big of an angle we would need to cut our slice of pizza in order to get that much crust, basically. Okay? All right, so I have this pizza, and I have two chords, F, G, and D, E. What do I know about those chords? They're congruent to each other, which means that the arcs they are creating are also congruent. Now, if this arc measures 1/16, and it's congruent to this arc, what is the measure of this arc? They're congruent, which means that this measures the same as the other one, 1/16. Very nicely done. Yesterday, when we were first talking about angles and arcs, we discovered that the central angle, that is the angle in the circle with the vertex on the center, this angle has the same measure as the minor arc that it's creating. So if this minor arc is 1/16, what's the measure of this angle? 1/16. Got someone at the back. Thank you. Because the measure of the angle that creates the arc has the same measure as that arc. Okay? That's what we discovered yesterday. Easy enough? All right, do you want to try number 1? Or do you think you got it? You want to try it together? All right, let's look at number 1. All right, here are 2 chords. What do we know about these chords? They're congruent, which means the measure of this arc created by this chord is the same as the measure of this arc created by this other chord. This arc's measure is x. What would be the measure of this arc? If this arc's measure is x, what would be the measure of this arc? X. That doesn't seem helpful, except when we add one fact from yesterday. The arcs in a circle, when you add them all up, you get 360 degrees, which means this arc plus this arc plus this arc equals 360. Yeah, and now it's an equation I get to solve. I may need some help with numbers. 296. I'm afraid to write it.
296.
296? 296, okay. I got the confirmation from 2 people. As soon as he is back. Thank you. And then we're going to divide by 2.
148.
148. Okay, thank you. I was already going, Yes, sir. The measure of each x is 148 degrees. Good. That's not the only thing we can do with arcs and chords, because we can bisect them. And when we bisect them, cool things happen to their measurements. The first one, in a circle, if a diameter or a radius is perpendicular to a chord, then it bisects the chord and it bisects the arc that the chord creates. So in a circle, if the diameter or the radius is perpendicular to a chord, then it bisects that chord. What does perpendicular mean?
Makes a 90-degree angle.
Makes a 90-degree angle. I'm going to write intersects because they have to touch. What did bisects mean? Cuts in half. Wait, I've got one. He needed to go, yes? Okay, so him first, yes? Thank you. So bisects mean cuts in half. Thank you. All right, so let's look at the picture. All right, here I have a circle. I have some diameter. If I look from A to B, it's a diameter, but if I look from the center C to point D, it's a radius. And so this works with either one. This diameter, or radius, is intersecting this chord at the 90-degree angle. This says when I have this setup, ladies, the measurement of the chord on this side is the same as the measurement of the chord on the other. And the measurement of this arc is the same as the measurement of this arc. Okay? That's what this says. Okay? If we know that we have a diameter or a radius, and we know it's 90 degrees to the chord, we've got some bisector happening. The next one is almost identical, except this time we're going to start with the perpendicular bisector of a chord. I've got someone at the door, please. Thank you. In a circle, the perpendicular bisector of the chord is the diameter or the radius of the circle. The first one you have to know you have a diameter. The second one, you don't have to know it's the diameter. It tells you after you look at it that you have a diameter. The last one. In a circle, or in congruent circles, two chords are congruent to each other if and only if they are equidistant from the center. What did equidistant mean? Huh? Equal distances. Yeah, exactly. Yeah, equal distances. So if I've got two chords and they are equal distances from the center, then that means that those chords are congruent. All right, when you're ready, flip the page, join me on the back. Let's do some examples. We'll get through as many of them as we can before time is up. We've got only about 10 more minutes, okay? So that you have 10 minutes to kind of... All right. Ready? All right, flip your page, join me on the back. What is that? Yeah, it's the symbol for circle. In circle P, the radius is 13. The chord RS is 24. Find the measure of all three of these things. I'm going to zoom in real tight here on this picture just so that we can see it. And I'm going to write down the things that we're looking for over here. Okay, so we're looking for the measurement of those three segments. All right, RT. RT is part of the chord. It goes from R to T, and the chord goes from R to S. What kind of line segment is P to Q? You're right, it's a radius. And you are right in that it intersects that chord at a right angle, which means I have a radius perpendicular to a chord. When I have a radius perpendicular to a chord, what happens to the chord? It bisects. It got cut in half. So that means this piece is congruent to this piece. If the entire chord, R to S, is 24, and I just cut it in half, how much is this piece? 12. Cut 24 in half. Yeah. Awesome. The next one I need to find is PT. PT is this little tiny one right here. Now I can draw a radius anywhere I want, and if I draw it in just the right place, it suddenly becomes helpful. So I'm going to draw a radius between R and S. Now, how did I get 12? So this entire length of the pink is 24, and it got bisected, cut in half. All right, I've drawn a radius from P to S. I drew it there because I have a right angle right here. Now I've created a right triangle. I know the measurements of this piece, and I know that every radius in the circle is 13. And I can tell you right now, without doing any work or any calculations, and I promise you this is not coming up as an answer because I've done this example a couple times already. I have this triangle pattern memorized. PT is 5. And you can get them memorized that fast too. Do you remember the thing called Pythagorean triples? I've got a few nods and a few shakes of heads. So Pythagorean triples are whole numbers that when I stick them into this equation, they're going to make the left side equal the right side. The bigger number has to go in the letter C. That's all a Pythagorean triple is. It's just groups of whole numbers that when I stick them into this equation, this side is exactly the same as this side. That's all it is. And I have 2 out of very, very many Pythagorean triples memorized. I have the 3, 4, 5 triangle memorized, and I have the 5, 12, 13. And I recommend that you memorize at the very least those 2, because those 2 come up a lot. They're going to come up a lot in this course. Saves you a whole bunch of Pythagorean theorem work. They're going to come up in Algebra 2 when we start doing trig. They may come up again in pre-calculus or college algebra if you're going there. If you're taking the TSI in the math, which you will have to do eventually sometime soonish in your life, a lot of the triangle questions are very quickly answered with those 2 Pythagorean triples memorized. 3, 4, 5, and 15, 12, 13. The sides of the right triangle. The big number on the hypotenuse. So let's pretend I didn't know that this was a Pythagorean triple. Okay, and let's use the Pythagorean triple, or the Pythagorean theorem, to solve for this little missing piece that I have right here. Okay? So I don't know what it is. I know what the other leg is, and I know what the hypotenuse is. The only one that matters for you to get into the right spot is the big number. Put the big number on C. All right, now I'm going to solve this. Square that. Square that. Bless you. I need help. 169 divided by 144. Because it's a Pythagorean triple, I know that it's going to be 25, but I want you to bust out your calculators or scribble it off to the side, long subtraction, and confirm it for me.
What do you want?
169 minus 144, so I can get a squared by itself. Yeah, calculator out to the rescue.
25.
She got 25. You're like confirming her because you can see her calculator or something on her? Yeah. Okay, 25. And the square root of 25 is?
5.
If you have even just those 2 Pythagorean triples memorized, you can skip all of this work. And it'll be acceptable as showing your work. Okay? All right. So now I have that one. Now I need this piece, T to Q. He's saying 11. How did you get 11?
I don't know.
What kind of line did you say P to Q was? It's a radius. You're right that it bisects the chord. It is a radius. So if P to Q is a radius, P to Q measures 13. But P to T is 5. So if this little piece is 5, the whole thing is 13. What does this have to be? So 13 minus 5. Whatever that is. 13,
8.
12. Okay, you're saying 8. 12. I was going to count on my fingers. So she says 8. I totally believe her. Yeah. You counted to double check.
Yeah.
Same. Hashtag when your math teacher counts on her fingers. Hashtag when she can still do it faster than you using a calculator. While counting with fingers. Alright, make sense? Alright. Let's look at this one. Same concept. We've been given a diameter, we've been given the measure of a chord, but this time we've been given the angle measure of an arc. Okay? So I know that this entire arc is 90 degrees. I also know that this chord is 8, and I know that the entire diameter is 12. Once again, I'm going to write down things that I'm looking for here onto the right side. I want the measure of the arc DE, I want the measure of segment FD, and the measure of segment AF. That was a fantastic conversation. Thank you. All right. I know that this entire arc is 90. I know this is a diameter, and this diameter is intersecting this chord at a 90-degree angle. When a diameter intersects a chord at a 90-degree angle, what happens? When a diameter intersects the chord at a 90-degree angle, what happens to the chord? When a diameter intersects a chord at a 90-degree angle, what happens? It divides in half. It bisects it. This piece is congruent to this piece. It also does that to the arc. So this piece is the same measure as this piece. When we come back, we'll find the measure of these arcs. Stay tuned.